It's a pleasure to be here, and I've had some great conversations with all of you. So today I'm going to be talking about multiple star formation, multiple star systems. So how many of you work on something related to stellar multiplicity? All right, good. So that went better than the last time I asked that question, which was total silence and no movement from the audience. So, so many of you may already know some of the things that I review here, but I will just go ahead and get started. For those of you who don't know why multiplicity matters, why you should care about this talk. So it turns out that multiplicity factors into a really broad range of stellar astrophysics. So for example, if you care about supernova or transient rates, type 1As depend upon the multiplicity distribution and properties. If you care about exoplanets and exoplanet architectures, there's some evidence that the distribution planet properties depend upon not only on the host star, but vary between single and multiple star systems. So in order for us to understand those planets and their properties and even the frequencies of life, we need to understand stellar multiplicity. Of course, if you care about star clusters, multiplicity matters. In particular, stellar dynamics is influenced by the multiplicity of the cluster, because these systems store a huge amount of potential energy, which you can extract or store and thus modify the evolution of the cluster and its properties. There's been some recent work suggesting that stellar multiplicity within the cluster in dense clusters might be critical for the formation of intermediate mass black holes through stellar collisions, so that's pretty intriguing. And last but not least, I don't want to leave the cosmologists out, but there's some idea that maybe the reionization of the universe was influenced by stellar multiplicity, where if you have these massive multiple systems, massive stars, you may, through these few body interactions, eject massive stars from your galaxy, and that actually enhances the reionization because they're kicked out and they are much more able to reionize. But in order to do that, you need to start with a population of multiple star systems. All right, so are you monitoring the Zoom so in case anyone asks questions, you can see what's going on over there? And there's no issues that they've all been able to see and hear?
They're all quiet.
They're all quiet? All right, so they've all gone off to the kitchen to have a cup of coffee. All right, so here's my outline. First, I'm going to start with some family photos. What I mean by that is stellar multiplicity is one of the few topics in astrophysics where you can go out and look up at the night sky and see the thing that you're studying with your bare eyes, amazingly. Then I will talk about how stars form and specifically how do multiple star systems form. So my background is in computational astrophysics and in star cluster formation. So I will talk about some of my work in what we are able to learn from the simulations that we can't maybe directly access from the observations. And then I will close on what does it all mean for planet formation. So let's start with some family photos. All right, so about half of all stars have siblings, maybe a little bit more than half. The most common architecture is a binary system, so you have two stars. Anybody know off the top of their head a binary star system? Just checking. What? Did somebody say Alpha Centauri? We're getting there. All right, so we'll start with Sirius. So the brightest star in the night sky is actually a multiple star binary, and it's a separation of 20 AU. If you want to find Sirius, you can find it by finding the Orion constellation. Can you guys see Orion down here? Yeah, some, okay. Yeah, so usually you can, if you can identify Orion, you can figure out where this binary system is. Of course, the most famous one, particularly if you've been keeping up on your Star Wars, is the Tatooine system. And I think, this comes from the 1970s. And at that point, the idea of a planet in a multiple system was science fiction. But today, we know quite a number of planets that are in multiple systems. So that's pretty exciting. All right, so what about other architectures? We have triple star systems. And I've drawn it this way intentionally because most triple systems in the field are what we call hierarchical triples. So you have two close companions and then a tertiary that's further away, which is a more stable configuration. Anybody know of any triple star systems?
Alpha Centauri.
Alpha Centauri, all right. So that is now one of the most well-known ones, which is the one nearest to our sun. And it has it is a hierarchical triple, so the close pair has a separation of 11 to 35 AU. It's a bit eccentric. And then you have a very wide, low-mass companion, 13,000 AU away. So there's been some rumblings that there might be a planet around Proxima Centauri. I don't know where we stand with that at this point, but this system would be the obvious candidate for where we would want to start looking, given how close it is to us, relatively speaking. All right, so you should be able to see it down here. It's near the Southern Cross, so you should be able to see it with your own eyes. And it's, I think, it's pretty bright, the third brightest star you should be able to see down here. So if any of you read sci-fi, you might know this other famous triple system from the three-body problem, Trisolaris. Has anybody read this book? Some of you, some sci-fi fans. Yeah, so in this book, it's about the rise and fall of civilizations, basically due to the chaos of the dynamical interactions of these three stars messing with the planet. And I think in reality, this would be very unlikely because, as I said, these triple star systems settle down into a fairly stable configuration of hierarchical configuration. And so once the star system's in that configuration and the planet is around whatever it's the tertiary or maybe around one of the other ones, it should be pretty quiet, right? It shouldn't have this wild changes in behavior. All right, so there's another famous triple system, which you may not know about, T Tauri. So T Tauri is the fiducial young star. And it turns out that this is not so fiducial. So T Tauri is actually highly variable. It's a young triple system. It has a total mass about 4.5 solar masses. So two of those stars are about 2 solar masses, and there's a 0.4 companion. You'll also notice in this diagram of T Tauri, it's showing the disks and outflow orientations, and you can see that they are not aligned. So there's definitely some interesting dynamics happening in this triple star system. And T Tauri is associated with, or at least nearby, the Taurus constellation. All right, there's one more type. The only other type that's longish term stable, which are quadruples. And they are stable because they basically act like two binary pairs. Anybody know of any quadruples? Yes. Okay. I don't know what that name that goes with, but the one I know is Mizar. Yeah, so it's actually one of the first binary, well, it was first identified as a binary, and one of the earliest ones to be identified as a telescope. And then when HST and some other observations targeted, each of those individual stars were resolved into a second binary component. So there's 4 stars, and it's also an easy one to identify because it's in the Big Dipper. So that's pretty cool. All right, so with this zoo of different types of multiplicity, you might be wondering, well, where does our sun fit in all of this? So what we know is that multiplicity does care about stellar mass, and that the multiplicity fraction, so if you just count up the number of binaries, triples, and quadruples to the total number of systems, this multiplicity fraction is a strong function of primary mass. So if you have our sun here, he says about maybe half-ish of our stars have at least one smaller star companion. And if you add in sun-like stars that are companions to more massive stars, then you get maybe a bit more than half of solar-type stars are in multiple systems. So another measure that we might use is the higher order counting. So the triple fraction, which includes triples and quadruples to the total number of systems. That is also a strong function of stellar mass. And here in the case it's much rarer for sun-like stars. Maybe only about 10% of sun-like stars have at least two smaller companions. But as you go to high-mass stars, almost all high-mass stars have siblings. So the multiplicity fraction approaches 100%, and a very large fraction of those systems are higher-order systems. So how do stars end up in these configurations? And the answer is simple. They were born that way, right? So by and large, what we know is that multiplicity is set at formation. There's a little bit of evolution, but by and large, there's very little dynamical change after the end of the star formation process. But one difference between these stellar twins is that in case of stars, but not children, is that in many cases, one of the stars ends up being much, much larger than the other star. So we also like to measure the mass ratio of these stars. And that is maybe gives us some clues about how they form. Okay, so how do stars form? All right, so here is the obligatory star formation stages. You guys have probably all seen this summary of star formation. You start with a dark cloud. You form some overdensities or dense cores. They gravitational collapse. Angular momentum causes the formation of a disk and a bipolar outflow, which ejects material. Over some amount of time, 100,000 or a million years or so, you clear up this material and you end up with a T-Tauri star. So again, there's a little oops here because this whole schematic is showing you T-Tauri as a fiducial star. It's showing it as a single, very well-behaved system, which we know is not true. But in any case, after this T-Tauri stage, we're left with this remnant material, which goes on to form planets. There's maybe also a little bit of oops there because now, with these fantastic ALMA images, it seems to suggest that planet formation and star formation are happening much more contemporaneously than we thought. So maybe star formation and planet formation are happening even down to back here. All right. So, all right, eventually we get a nice solar system out. Okay, but this picture leaves out a lot of things, right? So what about stellar multiplicity and companions? This is the let there be a core picture. So how do you actually get these overdensities or filaments? What about high mass stars? This is supposed to represent low mass star formation. And so there may be some important differences there. And of course, what about neighbors and dynamics? Because most stars form in clusters, not as an individual star separately. So simulations can help us piece together and model this picture in all of its glorious complexity. So I'm going to show you a movie from the StarForge collaboration. It's going to be a 3D rendering where this is showing you mostly the gas density distribution. So whiter things are denser, but it also factors in the temperature. And so over time, you'll see some changing colors, which will, for example, green will indicate ionized material. So let's see if the music is working. You can see collapse is beginning. Here's where a young protostar is. You see these filamentary behavior. You see very strong clustering over here. So you'll also see when the feedback turns on. This calculation includes magnetic fields, radiation, stars, outflows, winds, and supernovae at the very end. This whole thing is about 20,000 solar masses, so maybe not quite a giant molecular cloud. And it spans maybe about 5 orders of magnitude in dynamic range with 2 × 10⁷ cells. So you can see outflows happening. You You see this nice variation also. They're not entirely smooth. They move, they change directions, they interact. When the massive stars form, winds start. You can see these bubbles created. This whole thing is spanning about 8 million years. It continues to go on actually for a little while longer as the gas is being cleared, and this ultimately forms an association. At some point there's a flash when the first supernova goes off. You can see over time the gas is being cleared, and you are getting a revealed star cluster here in the middle. Okay. So, why should we believe that beautiful movie? Starforge has a number of advantages over past calculations. So one is this full physics. You could see all of these different processes which we think are important for star formation have been put in here. That means that there's also no magic stopping time. We have not decided, okay, we've run out of computer time, we're done with this calculation, or we've run out of patience. They run all the way until the gas is dispersed, and so there is no magic time. This is the final masses when the stars have stopped accreting. So we have self-consistent dispersal due to this feedback. The other metric that we like to show is the stellar initial mass function, and that's shown here. You have the black from Starforge. It resolves approximately down to the brown dwarf limit, and it follows very nicely along the kind of standard Chabrier type IMF distribution. The other thing that seems to agree reasonably well is the star formation efficiencies. So star formation within molecular cloud is relatively inefficient, usually with only a few % of the mass turning into stars. And we can plot that in black as a function of time, the true star formation value. And then these error bars here are observed values. So if we just take this orange line there, this is inferred from local regions from YSO counts, just counting the number of young stellar objects. And we can do the same thing in Starforge, and we get something that nicely agrees. We can also do a radiative Bremsstrahlung calculation in green, which agrees pretty well. So overall, the influence of all this feedback and physics is that we seem to be doing a pretty good job reproducing what we know about observed star formation. Yes?
Should I be worried about the fact that it seems rather shallow, especially in the high mass end, in comparison with typical observed claims from like Krupa or Salpeter or whatever, or is that within the noise?
I think that's mostly within in the noise, but we do find there is some sensitivity, and also in terms of the different simulations. If you go to a more massive cloud, we get a slightly different answer. So there is some environmental sensitivity with that. But yeah, you can be nervous about it. But yeah, it's something we look at. But by and large, I mean, that's pretty good. So if you've seen other calculations report the IMF, you've maybe seen these large binned histograms that you can kind of fit whatever your favorite power law is to it. So by contrast, I mean, this looks pretty good to me. Yeah. Any other questions? Yes.
How bound was the cloud to begin with?
How bound? That's a virial parameter of 2. So we've also run different virial parameters, so it's like marginally-ish bound. Yeah. Okay, so that was how stars form, but the topic of this talk is how do multiple stars form. So we can dig into that process a little bit more now. So we can summarize the way to form multiples in terms of 4 different mechanisms. I'm going to group 2 of them together, which I'll call core or filament fragmentation. So these are separate, independent gravitational collapse events that happen within usually the same bound structure within a core or filament. And they form systems that are initially widely separated. So we're talking about 500 or more, usually a couple thousand AU separation. So you can characterize this type of process by gravitational fragmentation. So you guys know about the Jeans mass, the von Ebert mass. There's an equivalent gravitational fragmentation criterion for a filament, which might be less familiar, but it's the same deal. It depends on how thermally supported that filament is and how high the column density or how dense it is. So very similar to the case where, the Jeans mass type argument. The other main mechanism is disk fragmentation. So the idea is that through this accretion process, you form a massive disk in which material builds up, and you get independent gravitational collapse within those disks. And they're formed within the disk, so that initial fragmentation tends to be much closer, less than, say, 100 AU. The physics there is dictated by the Toomey Q parameter. So the warmer the disk, the less massive it is, the more stable it is. But the colder it is, and the more massive it is, the more likely it is to gravitationally fragment. The last one is capture, so the dynamical formation of systems that might initially not have been bound, they form separately, and through this dynamical evolution of the cluster, they're brought closer together and are captured into an orbit. And so that might have a range of different properties, but usually we think it takes place at later times after you have these independent collapses, you have these disks, things are dynamically moving within the cluster, and often this may be associated with cluster dispersal as you're kicking out the gas, so at later times. Yes?
Does the presence of gas help you have a slightly different version of dynamical capture where it's sort of, drag against the gas?
It does, actually.
Shear, et cetera,
yes,
capture?
It does. I'll show you a picture of that earlier, but yes, you can characterize the capture, well, at least you can have orbital evolution when there's gas there much more easily. Yeah. Okay, so for all those mechanisms, the good news is that we have observed all of them, or at least we have alleged, fairly convincing examples of all of them. So here's one example of core fragmentation. This is B5. This was followed up with the BLA in 2015. And it resolves into what looks like 3 compact structures together with a protostar. And if you look at the gas dynamics, you find that each of these structures is independently bound, and their velocities are low enough that they are all together bound in a single system. So this appears to be forming a quadruple star system. And we see these kinds of things also in simulations. This kind of wide turbulent or filament fragmentation is fairly common. This was a movie, but it's not working right now. In any case, another example is disk fragmentation. This has been predicted by models for a very long time, decades, but it was really only in 2016 that we caught it in the act, so to speak. I think this is a pretty convincing case. Here, this brightest one here is not necessarily the most massive, it's just probably the one that's accreting the most. So you have what looks like it's already turning into a hierarchical triple there, where you have 2 closer ones and one more widely spaced one. So again, simulations have been predicting these for quite a long time. Here's one from Matthew Bates simulations. So I also like to show simulation examples, especially if someone in my audience has done a calculation. So I'll show one of Daniel's examples. This is in the context of protoplanetary disks. So you can see how the fragmentation develops. Okay, so the gist of it, right, is that as the disk goes unstable, you begin to see the spiral structure, and those spiral structures begin to fragment. And it's no accident that they're fragmenting out here and not in there, because this is where the coldest parts of the disk are. Do you have any more comments to add about your simulation, Daniel?
I made this one for teaching demonstration.
Yeah, it's very useful. I also show it to my classes. But yeah, it's very nice. So in the star formation context, where the disk properties are a little bit different, you wouldn't get like 100 fragments. You might only get a few, but it's the same kind of process that develops. All right, the last but not least is formation by capture. So this is an ALMA observation for 2018. And you can clearly see that there are two disks there, so two young stars with disks. And then you see this very large strip of material, which should remind you of a tidal tail, because it is. So this might even look like interacting galaxies to you. Same kind of physics, where these systems seem to be interacting and being captured into a bound orbit. So we see this in simulations. This is an example from a standalone calculation where they basically threw two disks at one another. We also see some of this in turbulent cluster calculations. Here's an example from that. All right, so you can see that this secondary and tertiary are actually coming in from further away. They get captured in and start to form a hierarchical system. There's a sort of dance going on at the beginning as they try and settle down. It's a bit hard to settle down when there's all that gas there and there's a disk there, but eventually they will settle down into some kind of hierarchical situation. Okay, so lessons, yes?
Sorry is it okay to ask another?
Yes, yeah, go ahead.
Yeah, sorry. So, I mean, the standard lore if you have point particles, right, is, you throw three of them together to get a binary, because energy has to be conserved, so something has to be ejected. But here, is there enough energy dissipation from the gas being ripped off that you can actually throw two stars at each other and they will stick together?
They will stick. Here it seems, yes. Yeah, as we'll see in a minute, the evolution of the orbits it is sensitive to what the gas is and how much gas is there. Here, once things are coming in, that's usually, unless there's a close encounter, they're not going to be kicked out, because the initial velocities of the stars forming in the cluster are actually not that high. So if the turbulent velocity is a kilometer or a few kilometers per second, then these stars form. They're not really too ballistic, a little bit, but yeah. Might be different in a much denser star cluster though. Okay, so lessons from simulations. So ideally we would just go out and observe the answers to all of our questions. But it's pretty tricky. And so simulations can be very useful, particularly for multiplicity when we have challenges from statistics, challenges of resolution. So simulations can help quite a lot. So one question we might have is, let's suppose we observe a multiple in the field. Can we predict or post-dict how that multiple came to be? What mechanism formed that multiple? So how can we distinguish these different formation mechanisms at later times? Right, so ideally, we catch them in the act. But as I said, most of the multiplicity is set at very early times and is very hard to catch them in the act. We also have limits on resolution. Even with ALMA, it's very hard to detect very close multiples, or detect or measure the disk properties on very small scales, for example. And of course, at that time, the gas is also optically thick, so our best bet is radio. So we have a number of limits at these very early times. So one thing simulations might suggest is maybe separation is a key. So there have been a few surveys of nearby star-forming regions and the multiplicity of protostars. so the best we can do for catching them in the act. So interesting, as you look at these very young systems, it does not look like the multiplicity distribution in the field. So for example, the separation distribution for solar type stars is a nice log normal, but in these local regions, there appear to be two peaks. So one of them, potentially the close one, is due to disk fragmentation, or maybe dynamical evolution. And the other one could be this turbulent core or filament fragmentation. So, but what simulations tell us is that this dynamical evolution happens very rapidly at early times. And so just because something is close in the field, or even close when it's very young, doesn't necessarily mean that that is from disk fragmentation. So pairs seem to migrate to close separations, and this is due to a mix of this gas accretion and dynamical friction. So the orbit can shrink quite quickly. By quite quickly, it could be 100,000 years or a few 100,000 years. So something can start out at 10 or 20,000 AU and approach tens of AUs rapidly, quite rapidly. So unless you can catch it actually fragmenting, it is very hard to say, even for young systems, what the origin of a multiple might be. So we need something else. Another possibility is angular momentum. So again, looking at young systems, protostars, we see that many of them, like T Tauri, have misaligned outflows, right? So they're not all nicely lined up, but they can be perpendicular. You can make a distribution, a cumulative distribution of projected angle between outflows. You find that it is approximately random or even anti-aligned. This is something that we can reproduce in simulations. So if we have systems that form from turbulent fragmentation, there's no reason for their angular momentum to be correlated, because if they start at wide scales, they're seeing different gas, accreting different gas, and there's no reason why they should be lined up. So this is maybe one signpost. We see it both for outflows and disks, which gives us maybe a little bit of more timeline for the observations, because we can look at slightly older sources and see instances where you have quite a lot of misaligned disks, even when the outflow is not present anymore. But there's only, after that initial formation time, the outflows are gone, the disks are gone. Maybe planetary system architecture and orientations will tell us something. But the other possibility is stellar spin. So a lot of these calculations tell us that this misalignment can be preserved in the stellar rotation, so that if we could go to the field star population and measure the stellar spin orientations, maybe that would provide a clue. So if we saw that, we might say that those form from turbulent fragmentation rather than, say, disk fragmentation. It might be difficult to disentangle dynamical effects, because if something is captured in, it might be the same kind of deal. It could be captured into a close orbit, so maybe we would see that as well. But there are other processes that resist and tend to align over time, magnetic torques and tidal torques, if things are close enough. So that might erase this residual initial birth signature. There's been some attempts to do this in observations. There's a paper from 1994 where they purported to show that wide binaries that were more widely separated had more misalignment in their spin orientations, and close binaries tended to be more aligned. A reanalysis of that data recently has said that using more statistically rigorous techniques, you really can't tell that. You cannot infer that from the data. So I think this is still an open question. It might be promising, but it's a pretty hard observation to make from the stellar data. All right, so another lesson from simulations that we would like to learn. So what is the role of environment? So as we look at stars around the galaxy, they have, there's very little indications of what conditions they might have been formed under. As we saw in the beginning, stellar feedback erases that birth cloud, erases the initial conditions. And so it's very hard for us to back out true impact of the environment, the local initial environment, on stellar multiplicity. But this is something that we can attack with simulations. This is also a hard problem for simulations because we need statistics, and doing these calculations tend to be very expensive. So there is some limited environmental changes we can probe with observations in these local regions. One of them is stellar density. So here is the combined populations of Perseus and Orion broken up into multiples in what is considered low stellar density regions and ones with high stellar density. The size of the error bars gives you some sense for how poor the statistics are from observations. But interestingly, there does seem to be some effect where this is predicting from the observations that higher density environments give you more multiples. But then on the other hand, so this is age as a function of time, so potentially there's some age evolution and density evolution. If you only look at the closer systems, so only from 20 to 1,000 AU, a lot of the signal goes away. Part of that could be because this initial large signal, this large difference, could be because there's confusion. And so in these higher density regions, you are accidentally characterizing something that is a multiple just due to a chance alignment. And that is very hard to weed out of the data because we don't actually have orbital information for these stars. So this is something we can look at in simulations where we can actually tell if stars are bound. We can look at their history, we can look at the environment very well. So this brings us back to Starforge. So I have another movie for you from Starforge. Some of the fun things you can do with particle and cell codes. Yeah, so this was made by a postdoc who worked with me, David Gusinov, and he actually said that he would write all of our names in the gas, and then we could have our own personalized version of this, which I should definitely have him do because it's super fun. Yeah, so much fun, so much fun. All right, so, but that was not the calculation we're analyzing. That would be, yeah, asking a little bit too much. Okay, but here's the calculation. Again, this image here is from the one you saw the movie earlier, where we're following from the beginning with all the feedback until cloud dispersal. And at this point, we can actually determine what is in these bound systems and when it's actually stopped accreting. So the plot on the left is showing you the multiplicity fraction as a function of mass. The observations are in black. So you can see the simulations are getting that same trend where there's a very strong dependence on mass. If you incorporate things like selection effects, they may be underestimating the multiplicity actually, which is potentially good because these systems in Starforge, as great as Starforge is, it is not resolving protostellar disks, it's not resolving accretion disks. So all of this multiplicity is coming from core and filament fragmentation and dynamics. So in some ways, it's a very nice numerical experiment because we are isolating only one type of formation mechanism and seeing how well that reproduces the observations. So it does pretty well. This is the companion star fraction. But as I said, there's no disks. And that means that it's underproducing low mass binaries, particularly near this resolution limit where we just don't have enough mass resolution. However, one of the advantages of Starforge and the ability to do these large clouds is that each of these calculations is forming thousands of stars. And that means for the first time, you can select out only the solar type stars and look at those statistics. All right, so that's where we should be complete. And we still have enough statistics to actually look at what's going on. So here are predictions for the mass ratio on the left compared to the observations, the black points, and correcting for the observational biases, we get it's basically flat. It's a pretty reasonable agreement. Similar shape between the simulations and observations on the right, showing the eccentricity of these systems. Again, close things here have this low eccentricity, and as you go to high eccentricity, there's many more of those systems. All right. So unlike in the observations where it's very hard, we can plot the multiplicity as a function of time. And we see in StarForge the multiplicity fraction actually decreases over time. The observed multiplicity fraction in young clusters is the black point, and sort of arbitrarily placed there for time. So it's kind of in the middle between the very early higher multiplicity fraction of StarForge and the late time low multiplicity fraction. And it's kind of interesting, this is quite a big effect in one simulation to have such a large change in multiplicity by a factor of 2 over this time scale. And what we think is happening is that this is primarily a result of the stellar densities of where these stars are forming. At early times, the stellar densities are low because there's not many stars in the population yet. At late times, you have high stellar density, particularly in that central cluster. And so if you redo this plot and you plot the multiplicity fraction as a function of the stellar mass density, you can see that there is a clear correlation with what the local stellar density is while these things are forming. So again, the observations are in gray, and maybe the observed regions are kind of in here. It's a bit hard to tell because we don't have the volumetric information. So it's okay agreement. But this does make a prediction that if we were to go to denser environments, that the multiplicity fraction would go down, and lower density environments, the multiplicity fraction should go up. And then we can do this same kind of plot, but just looking at the stars that form in these different types of environments. So at the most dense environment, which is kind of at the peak star formation, you get this very low multiplicity fraction. At early times, the least dense, you get a higher fraction and with some decrease. So there is some combination between the conditions when these multiples are forming and the dynamics that is happening, right? So there is some evolution at the low density environments. It takes some time for those multiples to settle down into their configurations. But by and large, a lot of it just seems to be about the local density at formation. Okay, so that was one cloud. But in the StarForge suite, we looked at a huge range of properties. We looked at different Vero parameters. The fiducial one was 2. We looked at different surface densities for these star-forming regions, different magnetic fields, mass to flux ratio, different initial stellar radiation fields, so the local environment, say, versus a high radiative environment, which might be more applicable closer to the galactic center, and different metallicity by a factor of 100. So in the first paper where we looked at this, we focused only on the bulk properties, like the efficiency and the stellar IMF. It turns out the stellar IMF is remarkably insensitive to any of these things. There are a couple of things like metallicity, maybe local magnetic field. We see a little bit of a trend, but within the statistics, and particularly statistics compared to observations, it's remarkably insensitive to all of these properties. So that's great because that's what we see in observations. But then the question is, what about stellar multiplicity, and is that the same or different? So we have this for all of these different conditions, and then we've made a summary table, which I will walk through. The key point here is that even though the IMF is remarkably insensitive, the star formation efficiency does change, which means the stellar density varies across these different conditions, which automatically is going to suggest to us there will be some differences. All right, so we summarize this in a table, which is a bit much to confront you with, so I just focus on one row at a time. So initial turbulence. So if we increase the amount of turbulence, right, so the gas is more turbulent, then that means the star formation goes down, star formation efficiency goes down, so the stellar density goes down. So that means that as we increase this Vero parameter, the multiplicity fraction goes up, all right? So again, there's this dependence on stellar density. Same thing with column density. As you increase the density of the cloud, the star formation efficiency goes up, the stellar density goes up, and that means the multiplicity fraction goes down. Same thing, it's the same story every time for the magnetic fields. As you increase the magnetic energy, there's more magnetic support to the cloud, star formation becomes less efficient, and that means that the multiplicity fraction goes up. So the systems that do form are simply not going to be disrupted as easily in this low density environment. There's also whether you like boxes or spheres. So we checked the conditions if you start with a sphere, like the simulation I showed you, versus a turbulent box, which represents a piece of the cloud. You can see right away that many groups that are doing turbulent boxes as clouds will get a much more distributed star formation. So the average stellar density is lower, and as you'd expect, that leads to a higher multiplicity fraction. The other two, metallicity and radiation, are a little bit more complicated because these are the two cases where there is some subtle IMF variation, which makes it a little bit more difficult to compare. So for example, in each of these cases, you're experiencing a change in the characteristic or median stellar mass, and this has a bit of a nonlinear effect on the multiplicity. In the case of metallicity, it's not quite so clear that there's a correlation with stellar density anymore, but there is some change. With the interstellar radiation field, the temperature of the gas is changing, and the IMF changes a bit. So there is a mild increase in the multiplicity fraction. All right, so moving into less explored territory, what are the implications for planet formation? So thanks to ALMA, there have been a number of surveys looking at the properties of protoplanetary disks, and in particular, such disks in systems that are multiple systems. So the best case statistics we have is for the Orion region, where we can get a good number of disks to be able to do this split. What you can see is that compact binaries, or close binaries, tend to have smaller and less massive disks. All right, maybe this is no surprise, because if you have close things together, they're interacting, the disk gets disturbed, maybe it gets tidally truncated, and so you've removed mass from these disks. Wide binaries have the largest disks, which is maybe less intuitive. I think the answer is that systems where you have wide binaries could be binaries because there's just more mass in the system. So you have a core or filament where there's a lot of mass, you get two fragments, and then they're wide enough apart that they're not tidally truncating each other's disks, they're not undergoing close interactions, and so you actually have more mass in these systems and then larger disks. And then single star systems are somewhere in the middle. So we can move a little bit forward in time to class 2 stars. So this is showing the mass distributions of disks, class 2 disks in binary and single systems. These disks are probably the ones where planet formation is already underway. So this could be telling us something about the conditions while planet formation is starting to happen. So in this case, again, you have the close binaries have smaller disks as we expect, do these interactions or tidal truncation. But here, single stars have the largest disks. And that could be because eventually, as time passes, these wide systems do have some sort of closer interaction that truncates the disk. Maybe the disks in those systems just don't live as long, and so they shrink more quickly. It's not really clear what's going on here. I don't know why it stopped. Okay, now it came back. Okay. All right, so we can then speculate about planets. Does this mean that tight binaries have fewer or closer and are lower mass planets? This is a prediction, which hopefully we can begin to test. And this might also, again, predict that planets are more similar in single and wide systems. So we can try to compare architectures in cases where we think that a binary pair is far enough away that it basically acts like a single system. Yes, I have 5 more minutes. That's good, because I've reached my open question. Okay, so we're left with a series of open questions, which we need more simulations and observations to entangle. So what is the fraction of multiple systems from each formation mechanism? We're still working on this with simulations. StarForge is great, but it's still really hard to simultaneously get statistics and resolution to resolve disks and turbulent fragmentation at the same time. How does multiplicity change in extreme environments? StarForge looked at an interesting but a fairly narrow range in environments. We're not saying anything about, say, multiplicity in the galactic center or in globular clusters. That's an open question. How are these planet formation and properties different in multiple systems? Extending the calculations to look at planet formation is likewise a really hard problem. And people who are doing planet formation calculation usually start with simple conditions, so it makes it hard for us to examine it. But there may definitely be something interesting in terms of differences between singles and multiples. And if at minimum we see this kind of difference in the disk sizes and masses, right? So there's probably something that's different, and pinning down quantitatively exactly what it is not clear. So altogether, if you take away anything from this talk, most stars form in multiple systems, including stars like our sun. There's very strong mass dependence in multiplicity, triple, and companion fraction. We no longer need to speculate about these mechanisms. We have caught them in the act in all cases. We see them in simulations, and right now it is mostly about pinning down some of the interesting details of how this happens and where this happens. The mechanisms of core and filament fragmentation seem to explain a lot of the statistics, but we still have discrepancies for which we need disk fragmentation, so we can't rule out one of these mechanisms as being unimportant. And I think simulations are doing reasonably well in terms of comparing with observations and making statistical predictions, really for the first time. And clearly there's some cool stuff that we're going to learn about planet formation in these systems, and that continues to be an open area of research. All right, I'm happy to take any further questions. Thanks.
Thank you, Stella. Are there any questions from the audience or from Zoom? Yes, for you.
So earlier on you mentioned about stars forming with different masses. Have you looked into the mass ratios and defining as it formed?
Yes. Yes, we have looked at the mass ratios. We have, in StarForge, we have an excess of low mass ratios, where things that are close to 10 to 1. And the reason is related to the lack of disks. So there's a number of things that dictate whether mass goes on the primary or on the secondary. And those processes are related to disks, and they're also related to local properties like magnetic fields, which can preferentially direct material onto one or the other. And so StarForge is not doing a bad job, but there is an excess there, so we think that's an area of improvement. So I wouldn't want to try and make too many predictions from the simulation data from that. Yeah.
Anybody else? Maybe I can ask one question before we go.
Of course, I've asked too many already.
Yeah, I'll get the next one. Yes, so you mentioned that there are 4 different mechanisms to form multiple stars. Is like a preference for any of them to form the really most massive multiple stars, or they can all contribute equally?
The most massive stars. Yeah, so Caitlin Crater, her work has showed that you can characterize disk fragmentation, the likelihood of disk fragmentation, in terms of 2-dimensional parameters that depend upon the infall rate and rotational properties. And so you would think that disks around massive stars tend to be heated, and so they should be stable. But in fact, even though they're heated, the infall rates are so high that the disk becomes so massive that in the massive star case, we think quite a number of those are likely formed from disk fragmentation. We haven't caught any in the act, so to speak, from the observations. But exactly what that breakdown is, we don't know. But we know there's some mass dependence.
Okay, thank you. it's already 1 and there's a me and there's another meeting here, so maybe we can keep on chatting
Yes.
artificially. So yeah, thanks.